Very excited to talk today with our founder, Jonathan Tooley, about an interesting subject that is super important to JTA. Not the most glamorous subject if you think about the context of AI agents and generative AI, but completely foundational. And even in my four and a half years at JTA, it comes up so much, and that's really around matching data. Could be company records, trying to aggregate data across different systems. And it's so important to so many different use cases that are very diverse, but the same underlying algorithms and technology. I've seen it used to help some of the largest organizations in the world align data from an ERP system to a CRM to do things like revenue recognition. We've seen it used to help marketing organizations consolidate and deduplicate records, so there's a really good foundation. So if you're using things like Gen AI, you ultimately have a pretty accurate source of truth about your customers, or even to build training data sets for machine learning models to do things like test out propensity, sales campaigns and whatnot. And again, having a very accurate source of truth. So I'm really excited to talk to you today, the architect of much of this in terms of a lot of this work around matching. And again, it's not the most glamorous use case in the world, but it's so foundational. And it has a pretty cool origin story in terms of some of the research that you did, 5-6 years ago, that was sort of the seed for a lot of this work.
I don't know what you mean when you say it's not glamorous. I think,
it is to us.
Call me a nerd. Maybe I'm a bit of a nerd, but yeah, text matching. Oh, that just gets me going. But yeah, no, I agree. I know what you're talking about. That it was many years ago now. It was a fun time. It was JTA was trying to solve a problem for one of our largest customers, and actually it was one of those kind of challenge accepted sort of things. The customer had said, look, we've been through a lot of consulting firms and they've failed to find a reliable answer to this. And I knew why, or at least I had a feeling why. And it was matching their customer data. But the scale of this company meant that they didn't have 10,000 customers. They didn't have 100,000 customers. They had tens of millions of customers.
Literally one of the biggest companies in the world.
And name no names.
Yeah, of course.
And it's one of these really interesting sort of algorithms, matching, because if you think about let's say you want to sort of do a match. You take a piece of information, you say, well, I've got to compare that now with all of the other things in this database. So you scan through that, let's call it 1 million, just to answer the question for the first item. And then you go to the next item and you scan through actually 1 million minus 1, because you don't have to compare something with itself. But you get the point that quite quickly what you're thinking of doing is 1 million comparisons. Actually, it's half that, because if you compare A with B, you don't need to compare B with A. But the point is, it's a quadratic thing. So this sort of algorithm explodes in runtime hugely. And when I first started work on it, I did a simple fuzzy matching kind of algorithm and ran it on a server, and I saw that the servers were actually pretty hot. They were able to do something like 20,000 matches a second. I thought, this is good. It's completely irrelevant though when you put it into the context of a quadratic. So I said, well, how, so if we have 1 million customers, it's going to run in, it might be running in hours, but when you get to tens of millions of customers, the whole thing kind of explodes to the point where, and I can't actually remember the scale, but it was of the order of years. And our customer said, we actually, it's part of our workflows and our processes. Ideally, we need this updated daily. It needs to be done within a few hours. And I thought, okay, so one server running very fast takes years. How on earth am I going to solve this problem? And I really didn't know. I was sort of a little bit at a loss. And so, of course, I started doing internet research, and then And the most ridiculous thing happened. I came across a paper, which was a medical paper, and it was where some doctors were looking to find when someone has a particular protein in their DNA.
Talk about quadratic scale.
Well, I thought, at first glance, you think that's completely irrelevant. What has got DNA and a medical application got to do with a large business and the way that they handle their data?
For sure.
But if you imagine writing, say, a company's entire contact list, their client list, in one great big long string, it's just a huge long string of letters, perhaps 1 billion letters. Well, a DNA string's something very similar. And so actually finding a particular occurrence, a particular protein, I thought, oh, actually this could help. Anyway, to cut a long story short, what they had done, which was really clever, was they thought, let's try and use graphical processing units, GPUs, to solve this problem, because GPUs they're basically thousands of miniature computers put on one chip. And each of these miniature computers can run a problem in parallel with the others. But the reason why I was so interested is this can really help to compute things quickly, but there's a but. These mini computers have to sort of more or less work in isolation, because if they start sending messages from one to the other, that will slow things down for a start, because that implies transference of data. But there's a really interesting issue with GPUs, and that is once each of these computers start running, the others don't quite know at what stage their sibling computers are at. So if they think, I better send some information to my sibling, what if that sibling's not at a stage where it's ready for that information, or it actually needed that information earlier? So you get these kind of conflicts of where things go wrong. So actually converting an algorithm to run on a GPU can be really simple. For what they were designed for, sort of producing images and manipulating pixels on a graphic, those tend to be quite simple. But for other types of algorithm, it's really hard. And actually what you have to do is restate the algorithm and say, how can I change this algorithm so that it can run on a computer, or it can focus on just a tiny part of this problem, and it won't need to know about the other parts of the problem. But when you're matching data, context is everything.
For sure.
So it's almost like a sort of contradiction in terms that you can use a GPU for these kind of things. But that's exactly what this paper on DNA did. So I thought, right, that's what we're going to do. We'll attack this, and we'll actually massively paralyze the problem and see. And of course, we can throw more and more resource at it. We can have 1 GPU, we could have 2 GPUs, we could have 10 GPUs. It costs money, but my client had said, can you do this in a few hours? And suddenly I said, absolutely, we can do this, because we just throw the GPU resource that we need at it.
Definitely.
Solves the problem.
Absolutely. And what I love about that example is it's important to note this was well before GPUs were as known as they are today in terms of solving different problems with language and text. You think about ChatGPT, it couldn't be more hot in terms of the notion of GPUs to train LLMs and whatnot, but this is a great example of years ago finding sort of a needle in a haystack, and a great example of JTA's innovative nature in terms of solving these problems and identifying technology perhaps before they become the norm to tackle such a mind-bogglingly large problem from a scale perspective, literally trying to match tens of millions of customers from one database against the other in a very mission-critical process, by the way.
And it was interesting because I was delighted. I thought, we had to go through so many hoops, and there's other hoops I can talk about that, but all the technical hoops we had to go through. But to an end user, to an end customer, I want you to match 10 million records with this other 20 million records over here, that actually sounds like a pretty trivial thing to do.
For sure.
And a lot of people just cannot comprehend the difficulties. And then so much can go wrong when you're matching data that can really bite you,
Sure.
if you don't consider some of these issues.
Sure.
That also complicates things.
The notion of data cleaning up front, pretty important, data normalization. What were some of the ways that you and the team tried to tackle that problem in terms of normalizing the data to make more efficient when it was actually matching and kind of solving some of that clean hygiene issues early in the process?
Yes, we did do quite a lot of that. So it was, company data. And one of the things that we kind of realized that, companies can have quite unique names like Google. I mean, it's really something a bit
Or
off
is
the
it
cuff. And, Alphabet, is it?
A computer
Alphabet?
might not know.
Oh, well, we could talk about that one. That's a very good gotcha. You got me there. That's a valid point. But yeah, no, things like in the UK, where I'm from, companies tend to be called limited, something limited. In the US, it might be something incorporated.
Right.
We're sitting in Portugal. It might be limited, limitada, but it might be an anonymous society.
Yeah.
So the way we describe the sort of legal entities across countries is different.
For sure.
But is it actually relevant? The name of a company, we typically have the name, so it could be, International Business Machines Incorporated. The incorporated is useful, extra information,
For sure.
but it's not completely, it doesn't define the entity.
For sure.
So, but you could also extend this because there's words like, let's say, we could have a company, Rab, Bruce Lockhart and Sons, or and Sons. You see that a lot, or and associates. Rab's Butchery.
Wouldn't shop there.
No. I couldn't possibly comment. But so there's words that have meaning, and can you then sort of, if you like, park those and say, well, that is all just a bit of noise that is making things complicated. So let's say the word butchery had been butchered, it had been misspelled somewhere. If you can identify that it's the word, clearly that's that word. And so, put that to one side, it makes the whole sort of matching, a lot easier. But it can also give you some really useful insight into things like industry. So if the word's got bank in the title, it's giving you clues. So you're then giving real value add. You're not just merging data, you're also kind of putting together some body of information about that might be really useful for
triangulation.
For triangulation.
For sure. Extra confidence scoring.
Extra confidence, and maybe we should explain what we mean by triangulation.
Absolutely.
Do you want to do that, or should I?
Well, from my perspective, triangulation is really, to your point, like you might have a probabilistic match, so it might not align exactly, but you could have other metadata that is associated with both names. So is it in the same city, country? Does it have the same postal code, the same domain from an email perspective, the same website, same industry? And all these things can compound to say, yeah, JTA Consulting SA is actually aligned to Jonathan Tooley Associates.
Exactly, and it amazes me how people do not triangulate. So when you've got a small name, ABC Taxis, an algorithm might say that's exactly the same as BAC Taxis because they're so close.
For sure.
And an algorithm might say, guaranteed, it's got to be the same. The similarity is just, it can't really be a coincidence. But that's absolutely not true. They can be completely different entities. Look into the metadata, and if you see one of them is based in Leeds and another one's in Paris, then you start to think, hang on a minute, are we being fooled by the algorithm making an assumption that it shouldn't?
For sure.
So it's never, ever taking things on face value.
Definitely.
What comes out of the algorithm.
For sure.
Check and double check, triple check from information that you might have inside your databases, your corporate databases.
Absolutely.
But what we do at JTA, as you know, is we often find that the data isn't good enough. So we'll do things like find the domain from an email for that corporate. We'll go and read their website.
For sure.
Our AI bots will go and read the website and start to learn a lot more about that.
Absolutely.
Which gives us, well, it allows us to do two things. Much better match rates with not just, with guaranteed accuracy. It's just, anyone can get a high match rate,
Definitely.
but a lot of them can be wrong.
For sure.
We can get a high match rate and guarantee that they're right, or we have confidence that they're right. But then we're building bodies of information that we could absorb into other parts of the corporate process further down the line that really helps a customer.
Absolutely. The enrichment engine, that's super important. You think about a great use case like, to your point, using AI to enrich data in cases where it needs to be enriched or enhanced is a really interesting notion where an LLM is very good at classifying industry from the About Us description page. Very, very good if it's been fine-tuned in the right way. And that can be helpful, exactly to your point, way further up the value chain, not just about aligning data and triangulation and confidence, but if you're a massive organization, let's say a big global sales force, you want to drive AI enablement, Gen AI kind of chatbots to help your sellers type of thing. You want to build propensity models to identify the best accounts. You need to have that enriched set of data to be at the foundation, because your downstream Gen AI application is going to be much better at finding and making the right recommendations if it understands things like the industry, understands all these sort of critical metadata attributes. So another example of where machine learning LLMs can help solve, well, what we find super interesting, but can somewhat be seen as a boring problem or not such a glamorous problem, but ultimately be so critical from a foundational building a great sort of data house, if you will.
It's fundamental. And actually, I have a funny story. I'll tell you the story. I have a friend of mine he works in the art industry, and the name of his company is, part of the name is Bristle, as in the bristles on a paintbrush. And he was contacted by someone who was using a CRM, actually probably one of the world's biggest CRMs, and they deployed matching engines and AI. And the salesman was talking to him about his company, but not talking about art, not talking about paintbrushes, started talking about the council and the city. Anyway, what had happened is they'd matched Bristle, as of a paintbrush, to Bristol, the city, and they thought that my friend didn't sell paintbrushes, but actually worked in the council at Bristol City or something like that. Sure. So there's an example of what a waste of time and money. A salesman is thinking he's trying to sell something to someone who works in a council, in the public sector. How wrong could they be?
For sure.
And it never ceases to amaze me when I look at my clients, how little they know. They've got millions of data points. A lot of them are very wrong. Or they might not have a domain name, they might not have a website address, they might not, very often the industry is wrong. Imagine you've got a really sophisticated sales process and the best sales folks in the world. If they think they're phoning to talk to some executive from a bank and they turn out to be party planners, it's just a waste of time and effort for everyone. And there's a reputational impact on the customer. People start sort of looking at the, companies and saying, "Oh goodness me, you're just wasting my time."
For sure. Or even supply chains, distribution, getting things to the right addresses. Like, it really comes down to aligning sort of this foundational data and having it an accurate source of truth. And that's a great example from a sales context as well. In terms of some of the techniques deployed, and thinking about firstly the DNA paper, then solving this quadratic problem with GPUs, so much more computing power in an early stage, but then also thinking about it, how could it be solved algorithmically as well with different mathematical techniques? What were some of the key algorithms? I know we talk about like Levenstein and cosine and things like that, but
that paper, I think, really the crux of that paper on DNA was the parallelization of Levenstein. And maybe for, just to sort of take a step back and explain what Levenstein is. To a computer, the concept of something being similar is quite hard to define algorithmically. You could write a phrase and a second phrase and say, well, how similar are these? That's quite hard to write a program, define similarity. It's a bit of a nebulous concept. But if you say to the computer, okay, I'm going to allow you to pick up a letter and move it, or maybe erase it and change it, or so you define little steps. What you say to the computer is, take the first phrase and edit it to be the second phrase, and tell me how many edits it needed. So if I just got my name misspelt, perhaps a letter was missing, it only needs to add one letter. So it can say, well, they are similar with a difference of one. It gives a numeric, it's a way of defining similarity as a number. And so that's good, but it's also horrendously flawed. So if I said to you, a human being, how similar is J. Tooley, my name, to Jonathan Tooley? You'd say, well, they're the same. I mean, anyone would say that. But Levenstein will say, oh, the difference between a single letter J and Jonathan, I've got to add an O, N-A-T-L. It's huge. No, they're not at all similar.
coming out of its ears.
That's completely different.
For sure.
So that algorithm has just been fooled by a ridiculously simple thing. Also, a database might store Christian name, surname, Jonathan Tooley, but it might store it as surname, Christian name, Tooley, Jonathan. Levenstein is going to say, not even close.
For sure.
But there are other algorithms. There's one called the cosine algorithm. And that can also be fooled, but that is an algorithm that the order of words is irrelevant. So Tooley Jonathan and Jonathan Tooley, it will say, are absolutely identical. But it can also be tripped up by other things, such as anagrams of letters. It might actually say, no, they're completely the same, but they're not. It just so happens that there's two words that are different, but one might appear to be an anagram of another. But what we did, and again, it's just taking this very cautious, careful, methodical approach to data matching. Why not deploy Levenstein, which has problems, and cosine, which has problems, but different problems, and then merge the results? Now, if you get an agreement, both Levenstein and cosine are saying match, we should look at it as a potential match. If they're both saying not a match, we should either reject it or think maybe, we will do further investigation, but for now it's not a match. But what if they're not in agreement? One saying, absolutely, it's a match. And the other's, no, it's not a match. That needs to go to a different part of the algorithm, and it needs to be looked at. And that's where we use the metadata from triangulation.
For sure.
Web scraping, doing further research, there's data enhancement, data augmentation, and even now, AI will go and use AI techniques to study, and we have models that learn. And we use the process of vector embeddings and...
well before they became so popular with ChatGPT.
Yeah, I mean, maybe about the same sort of time but before ChatGPT was really launched to the public, and but it was more of a kind of a black art. But a computer being trained on masses of data, reading lots of history and will immediately know that International Business Machines and IBM is the same thing.
For sure.
So if they see the two in different data sets, well, that's a potential match. Let's actually think about that. But this can be particularly powerful for, now here's an example that I think is very useful for companies. Often a company might have lists and lists of customers, but those customers are actually part of a group. They have legal relationships. They're closely tied together. And it's not yet perfect, but more and more we're getting very adept at using AI to unveil those kind of legal relationships. Parent-child relationships.
Sure.
And this can be amazing in a sales environment where, you know, often there might be a big sales deal going on, and it can be spoiled by something that happens to contradict, if you like, or so companies, the more data you can give a company, and actually then summarizing all that data into really usable insights for the people who are at the cutting edge of that business, whether it's the sales folks or other executives, it makes you look really intelligent, it makes you look slick, it makes you responsive to your customers, organized.
And a great example is, especially on the parent-child one, I'm glad you brought that up, because if you think about, let's say you're a massive organization and one of your customers is Blackstone, private equity conglomerate. How many companies does Blackstone own? Hundreds.
Absolutely.
But each of those companies are entitled to special discounts and pricing that have been negotiated with Blackstone globally, centrally, but very hard to map that out downstream, especially when you think about smaller businesses or medium businesses that they might own. So great example of just the organization element and how that can really help consolidate into a very accurate source of truth.
It's all about making our customers look good and making them smart, but also saving them a lot of wasted effort, massively improving the return on their investment for their internal workflows and processes.
For sure.
I mean, all of this comes about from just having much more intelligence, and that comes from great matching in a way that we can take their internal data and match it to external data, whether it's on the web or wherever it might be. It might be a data source that they've signed up to. But also internally, companies will have an accounting system, a marketing system, a customer database.
All siloed.
And they're all siloed. Exactly. That's the great term, what I was looking for. Matching makes it one understandable, explainable, cohesive data set.
For sure.
That unlocks intelligence.
Absolutely. What I love about the topic is it's, again, trying to align data, which sounds like it should be simple, because if you're a person looking at TD Bank or Toronto Dominion Bank, that might align, or Jay Tooley versus Jonathan Tooley. But to your point, for a machine, it doesn't necessarily natively pick that up, and especially with natural language processing, large language models, it's getting better and better if it's fine-tuned in the right way, if it has access to the data. To your point, if we're taking multiple approaches with data normalization, with different things like applying the right algorithms, GPU processing power, so many different foundational techniques and machine learning techniques to solve this really important problem, which then unlocks so many downstream use cases. It's a really fascinating use case that I think is often underestimated in terms of its importance downstream. So it's fun to kind of explore all the different applications, and definitely something to do an explainer on soon.
Yeah, well, I mean, we could talk for hours about this, but I think it would be, I would like to do an explainer on it, actually.
For sure.
And just sort of talk about some of the things that we've discovered that really, when deployed correctly, massively help
And make a difference
companies.
at scale.
Exactly.
Not solving for a list of 10 customers versus 20. It's millions and millions on a daily basis. So
Exactly.
it has to be scalable. Brilliant. Thank you, sir.
You're very welcome.